Good evening everyone. I welcome you all to the problem solving session of the NPTEL course on ice engines and gas turbines. So today is week 7 problems. Good evening. So we will see some problems related to flight, jet propulsion, and then we also have some problems on the compressors. The first question, the ratio of flight speed to exhaust velocity for maximum propulsion efficiency is dash. So propulsion efficiency is given by eta p is 2 by 1 plus Cj by u. So maximum propulsion efficiency means it is 1. So 1 is equal to 2 by 1 plus Cj by u, and if you have 1 plus Cj by u is equal to 2, then Cj by u is 1. That means Cj is equal to u, or we are asked for the flight ratio of flight speed to the exhaust velocity. So that is u by Cj. This is also 1. So with this, when u is equal to Cj, will there be a flight, or will flight take place? With this, with u equal to Cj, flight won't take place. So that means there won't be any thrust. And this is an extreme case where if propulsion efficiency is 1, then there is no flight. So we can have only propulsion efficiency tending to 1, and it cannot be equal to 1. And similarly, there is another extreme case where propulsion efficiency is 0. In this case, we have 0 equal to 2 by 1 plus Cj by u, and so for this to become 0, the denominator should be infinite, right? 1 plus Cj by u is equal to infinite, and this can be infinite when u is equal to 0. So again, that means there is no flight taking place. The flight is not null. Next question, in an ideal gas turbine cycle, the expansion in the turbine is represented by in a gas turbine cycle, the expansion in a turbine is represented by isentropic, isenthalpic, isobaric, or isochoric. Can you, if you know the answer, can you put in the chat box, or you can unmute yourself and tell? Option E, isentropic. So this is a Brayton cycle. If you draw in TS, we will have first isentropic compression, and then constant pressure heat addition or isobaric heat addition, and then isentropic expansion at constant entropy, and then we reject the heat at constant pressure, isobaric heat rejection. In case of PV diagram, we will have isentropic compression 1 to 2, and then isobaric heat addition 2 to 3, then expansion, then next question, a turbojet engine is powering a fighter airplane. Its cruise altitude is and Mach number are 10 km and 0.86 respectively. The ambient pressure and temperature are 223 Kelvin and 0.265 bar. The exhaust gases leaving the nozzle at a speed of 580 meter per second and a pressure of 0.75 bar. The outlet area of the exhaust nozzle is AE, is 0.25 meter square. The air mass flow rate is 46 kg per second, and the fuel to air ratio is 0.023. Determine the specific thrust and the propulsive efficiency. Define propulsive efficiency as the ratio of thrust power to power imparted to engine airflow. So the Mach number is 0.86, and with this we can calculate and the temperature of the ambient is also given as 223 Kelvin. So with this we will be able to calculate the sonic velocity, that is gamma RT is equal to, gamma can be taken as 1.4 since it is not given, and R is standard 287 into temperature 223. Can you calculate CEO?
$299, sir.
Yeah, 299 meter per second. Next, we have the velocity of the flight, that is Mach number into sonic velocity, that is Mach number is 0.86 into 280.
257.5.
257.5 meter per second. And now we have to calculate the specific thrust. So specific thrust is thrust by m dot a. So thrust can be given by m dot a plus m dot f into Cj minus m dot a into u plus pressure difference into area of the exhaust. Now we can neglect this because the air fill ratio m dot f will be m dot a divided by failure ratio. This is m dot a is 46 and into 0.023. This will be almost very less when compared to the m dot a. So we can neglect this. So we can have 46 into Cj is Cj. Yeah, it is given as 580. 580 minus m dot a is again 46 into u is 257.5 plus pressure exit nozzle pressure is 0.75 bar minus atmosphere pressure is 0.265. So these two are in bar, so to convert in Pascal I have 10 power 5, and then the exit pressure exit area is 0.2. Can you calculate the value of here?
26973.8.
26973.8. So this should be in newtons. Specific thrust is F by m dot a. This is 26973.8 by m dot a is 46.
$586.4.
586.4.
86. Okay.
Actually, I was getting 27.58 here, like into kilonewton. So can you check? This should be approximately 600. or maybe we should add the m.f value. M.f is 46 into 0.023, so this is 1.058. Maybe it matters. We can give here m.a plus m.f, that is 47.058.
Two 757 587. 2757 27587.
587. Okay.
600.
So this unit is we had Newton in the numerator and kilogram per second in the denominator. So this is both this and this are right. We need to now calculate the propulsive efficiency. Propulsive efficiency they are given, it is a different propulsive efficiency as the ratio of thrust power to the power imparted to the engine. So that is Fu by so propulsive power is force into this velocity of the flight, so that is Fu, and in the denominator we have the kinetic energy imparted to the engine totally. Energy imparted to the air. So this is 2 into 27587 into velocity is 257.5. This is 47.058. Cj is 580 square minus m dot e 46 into sorry 50%.
52%. 52.6.
I was getting 74%. So actually it should be around 74%, so this should be right. Next question. A helicopter is powered by a Rolls-Royce turboshaft engine with a takeoff shaft power of 700 HP, and the engine has the following data. Rotor efficiency is 0.74, gearbox efficiency is 0.98, fuel heating value is given, fuel mass flow rate is given. Determine the thermal efficiency of the helicopter. So this power shaft power is 700 HP. This is 700 into 0.746 kilowatt. Can you calculate?
522.2.
522.2 kilowatt. If you calculate the fuel power, it is 45 m dot f into calorific value. M dot f is 100 kilogram per hour. So to convert into kilogram per second, you have to divide by 3600 into calorific value is 45,000.
1250.
1250. This is in kilowatt. We had kilojoule for the heating value. And now rotor power is shaft power into rotor efficiency into gearbox efficiency. So that is 522.2 into 0.74 into 0.9.
378.7.
378.7 kilowatts. So efficiency is rotor power by fuel power. That is 378.7 divided by 522.2. Sorry, fuel power is 1250.
0.30.
So that is option B. You have any questions? The next problem. An aircraft flies at 900 km per hour. One of its turbojet engine takes in 45 kg per second of air and expands the gases to ambient pressure. The air-fuel ratio is 38 and the lower calorific value of the fuel is 41 megajoules per kilogram. So we need to find which of the following are true or false. The jet velocity for maximum thrust power is greater than 400 meter per second. So for maximum thrust power, so for maximum thrust, U by Cj is equal to 0.5. So Cj is equal to 2 into u. And you know u is 900 km per hour. So to convert that, we have to divide by 3.6. Can you calculate something?
500.
500 meter per second. So for jet velocity for maximum thrust is greater than 400. So this is true. Then specific thrust based on air intake is greater than 250 meter per second. So F is specific thrust is m dot Cj minus m dot A u divided by m dot E. So this can be approximated to Cj minus u, and this is 500 minus 250. So this is 250 meter per second. So now if you had this m dot as including fuel also, instead of just m dot a, it will be little more than 250. So this is also true. Next is the propulsive efficiency, again assuming maximum condition is greater than 75%. So this is a standard known thing if you have done earlier. For maximum thrust, eta p is 1 2 by 1 plus Cj by u, and for maximum thrust this is the condition, u by Cj is 0.5 or Cj by u is 2. So then we'll have 2 by 1 plus 2, that is 2 by 3 or 66.6%. So it is given it is greater than 75%, so that is false. So this is false. Next, the thermal efficiency is greater than 10%. So for thermal efficiency, eta T is half dot C, the kinetic energy imported, divided by m dot F. So here m dot F is Cj is 500 square and u is 250 square, divided by m dot F is mass of air by airfill ratio. So that would be 45 by 38 is airfill ratio, and calorific value is 41 megajoules. So this is 41 into 10 power 6. Can you calculate the thermal efficiency?
I'm getting 8.6 percentage.
Okay, 8.6 percentage. So this is less than 10%. So this statement is false. So next is thrust specific fuel consumption. T is Fc is equal to m dot F divided by F. So m dot F is 45 by 38, and this was in kilogram per hour. So kilogram per hour. No, okay, here in the answer it was asking kilogram per hour. So then we should multiply this with 3600 divided by the trust is so specific thrust we have 250, so multiplying with m dot a we can get the actual thrust. So that is F is equal to 250 into m dot a, that is, or we can directly write it here. So this is F is 250 into m dot a. M dot a is 45.
0.4.
So TSFC is greater than 0.45, that is false. Do you have any questions? Okay. For an extreme case of propulsive efficiency, that is 0 and 100%, which of the following statement is correct? Can you answer this? Aircraft moving with higher velocity, no flight taking place. Aircraft moving at a higher altitude. Aircraft moving with lower velocity and higher altitude. Sorry?
A answer.
Flight moving with higher velocity. Okay, I see your message that you have to leave it. So, so propulsive efficiency is given by propulsive efficiency is given by 2 by 1 plus Cj by U. So if it is, we can substitute 0 and 1 and see this. So this is 2 plus 1 plus Cj by U. I think we just solved some time back. So for this to be 0, then we should have 1 plus Cj by U as infinity. Then for this to be infinite, U have to be 0. Only then propulsive efficiency can be 0. Or we can also substitute U as 0 and then solve this. Efficiency, this is 2 by 1 plus Cj by 0, and this will be infinite, so this is 1 plus infinity, or this is 2 by infinity, or this is 0. So for propulsive efficiency to be 0, U should also be 0. U0 means there is no flight taking place, the flight is stationary. And similarly for 100% of propulsive efficiency, we will have 1 plus Cj by U is equal to 2, and then Cj by U is equal to 1, then Cj is equal to U. If jet velocity is same as the flight velocity, then there won't be any thrust produced at all. So then again there won't be any flight taking place. So the correct answer is no flight taking place. Consider the following equation. Please choose the correct expression for A. Propulsive efficiency equal to 2 into 1 minus A by aircraft velocity. So this is probably a little tricky, but we know that this is 2 by 1 plus Cj by U. None of the answers seems to be to be correct. So this 1 minus A by aircraft velocity is U. If you keep on uh, if you keep to solve this further, you will have u minus a by u, and then u square is equal to u plus cj into u minus a, and u square equal to u square minus cj u, so plus cj u minus of a into u plus cj. So then this and this will get cancelled, and we will have a u plus cj is equal to cj into u. So a will be cj u by u plus cj. But none of the answers seems to be giving this expression. So, but we know this is the expression, and if it can be pi, and then if this is the case, then it is velocity of the jet. If it is 2 divided by 1 plus a by aircraft velocity, then velocity of jet is right. Next problem, for multi-spool turbofan engine, the fan is driven by low pressure turbine, high pressure turbine, low pressure turbine, compressor, or none of the above. So it is driven by low pressure turbine. Which of the following suits for aircraft handling higher mass flow rate for lower altitude flights? Turboprop, piston prop, turbojet, both A and B. Actually, turboprop and piston prop are, for this case, higher mass flow rate and lower altitude. So both A and B are correct.
Yes, sir.
For only turbojet is for high altitude and low mass flow rate. Next is conversion efficiency of the aircraft engine is given by kinetic energy change divided by mass flow rate into calorific value. Kinetic energy change divided by mass flow rate of air into calorific value. Then in the denominator we have mass flow rate of fuel minus calorific value, mass flow rate of air plus calorific value. What is the energy conversion efficiency of aircraft engine?
I get option
Sorry?
A.
Option A, yeah. So we need to have fuel power in the denominator. So fuel power is given by m dot f into calorific value. Ganesh Kumar, can you please unmute yourself? You can, mute yourself. You can unmute when you want to talk something. Thank you. So next, which of the following is not an air braking engine? Turbofan, ramjet, rocket jet, turboprop.
Ramjet.
Ramjet is air breathing, right?
Okay.
It takes in air from the atmosphere.
Turboprop, sir.
No, turboprop also takes air. No?
Rocket jet.
Yeah, only rocket has their own fuel and oxidizer.
Oxidizer, yes, sir.
Yeah. is put in the rocket and then used. Ramjet engine will not have any moving parts, so it will have only nozzle and combustor and diffuser. Which of the following aircraft engine has convergent divergent nozzle? Piston prop, turbo shaft, ramjet, turboprop.
Convergent divergent nozzle with turbo shaft. No idea.
Ramjet engine. They will have a convergent divergent nozzle in the front, so nozzle. In general, vertical climbing of turbojet engine is achieved using intercooler, afterburner, reheater, multi-stage turbine.
Taking a turbojet aircraft engine is achieved using intercooler, afterburner, vertical climbing. What
So
is the
generally
vertical
for
climbing?
sorry,
What is vertical climbing, sir?
vertical climbing you would have seen in air shows, no? The flight will go just vertically upward.
The takeoff, like takeoff.
No, takeoff is just it will go in an angle, right? The fighter jets they will have some stunts. Maybe they use it
Oh,
in compact, and
yes,
but in
yes.
air shows you would have seen that they go vertically upward.
So they need more power. So multi-stage turbine.
Mm, no, multi-stage turbine is generally used for used during the entire flight. Okay, and intercooler is not a part of this turbojet. Afterburner is also reheater is also not. Afterburner is used for short uh, time when the power requirement is very high. So that is the answer. Short afterburner. So here after the turbine they will put more fuel and then use it only in the nozzle. So the turbine will not get this power. After the turbine fuel will be put. The idea is that more air will be there initially. The air-fuel ratio is very lean, and so there will be more air so that we can put more fuel and burn. But afterburner can be used only for a short time.
Okay, sir.
Okay. So next is about the turbo machinery. By considering the expression of turbo machinery equation, which of the following condition is valid for work producing device? Torque of the rotor is given by mass flow rate of the fluid divided by Cw2 into R2 minus Cw1 into R1. So here Cw is the world velocity component, R is a radius of the rotor, suffix 1 and 2 represent inlet and outlet condition for the rotor. Now we have to say which of the following is true. Cw2 into R2 is greater than Cw1 R1, or Cw2 R2 is less than Cw1 R1, or any one of the expression is 0 for a work producing device.
So, component. Using the roller of engine. No idea, sir.
Okay. So the for the work producing device, so this is kind of fluid power imparted by the fluid in the rotor, and at inlet and outlet we have um, the outlet energy will be less than the inlet energy, right? Because it is a work producing device. So at 2 the values will be lesser than the value at 1. So option 2 is right.
IC engines is somewhat easier than this gas turbine, sir.
Sorry.
IC engines are like somewhat easy than this gas turbines, I
Yeah,
think.
yeah, yeah. I'm also
Like,
working on ice engine, so I also feel the same.
but in college we have studied, but not in like this much deep, sir. We have studied like only the types, and we have went to some numericals, but not into the depth.
Hmm. Yeah,
Like
maybe ice
NPTEL.
engine you have already studied, and so maybe this course in the course ice engine portion is easy, and for
Yes,
turbo
sir, but
machinery.
not into the that much depth, sir. Like in this NPTEL classes, I am facing somewhat problems, sir. Like,
Hmm.
yes, sir.
So you are, I think we spoke in the last class, right? You are from Chennai itself, right?
Yes, sir. Yes, sir.
Okay, and you are not auditing. You are not writing the exam. You are writing the exam,
I'm right.
but
Yeah.
okay, but you are, that will not be taken for your semester
Yes, sir.
grading. Okay. Okay. In turbo machinery, which of the following option is correct based on the change in kinetic energy due to change in radius of the rotor blades? Reaction effect only, impulse effect only, both impulse effect and reaction effect, centrifugal effect.
Machinery, which of the following option is correct? Based on the changing character.
So when there is a change in radius, um, the kinetic energy changes because of what?
Changing. Yes, opposition is up to.
Centrifugal effect. Yes, it was more
Omega
used to.
square R, that's what I'm thinking.
Hmm. Since R is increasing, centrifugal force. Which of the following compressor is much suitable for low volume flow rates? Centrifugal compressor, axial flow compressor, both centrifugal and axial, none of the above.
Centrifugal compressors are for high volume. Standard compressor. B, option B.
No, actually centrifugal compressors are for low volume flow rate. So in centrifugal compressor, volume flow rate, low volume flow rate, low flow rate. But the advantage is that we can have high pressure ratio.
Mm-hmm.
In axial compressor, we will have low pressure ratio, but we will have high uh,
Handling of pressure ratio.
flow rate. Actually, during World War II, I guess there were UK and Germany. There were.
Sir, in the class they have mentioned as axial flow compressors can handle high pressure ratio,
Oh, is it?
like NPTEL
Actually,
class.
can you check? I also gone through the notes, but I remember this. Centrifugal compressor will have a high pressure.
No,
Axial
I
flow
didn't think.
compressor, maybe because of stacking, it is easy to stack next to next, and maybe totally the airflow that pressure ratio can be high. But one stage of axial compressor will have less pressure ratio compared to a centrifugal compressor.
Mm-hmm. Okay, sir.
So during Second World War, the UK and Germany had different uh, um, different designs for this fighter jet engines, turbojet engine. So Germany went with axial flow, and whereas UK went with centrifugal compressors. And then slowly they also found that centrifugal compressor is not very nice, good for them, and then they moved towards. Next is in a turbo machinery, which of the following option is correct based on the change in kinetic energy due to change in radius of the rotor blades? I think this is just okay, both are. In case of centrifugal compressor, the high velocity of the air is decelerates in blade passage is provided by diffuser, impeller, stator, all of the above.
All of the above. We can totally remove the friction loss and it is stagnation. That is a part of. Okay. The first one option D.
Sixth one?
Option D, I think so.
No. C, stator. Only in stator the high velocity air is decelerated and the pressure is increased. So diffuser is not a part of centrifugal compressor. We call it stator.
Yes, sir. I forgot.
So next is centrifugal compressor. The frictional loss in the impeller and diffuser leads to static pressure loss, static temperature loss, stagnation pressure loss, stagnation temperature loss. Answer is stagnation pressure loss.
Stagnation pressure loss.
Inducer is a part of the diffuser, stator, volute, impeller.
I have no idea.
Impeller. A centrifugal compressor without inlet guide vanes, the flow enters into impeller eye. Axially, radially, or both axially and radially, can't say. Where C is absolute velocity, CA is axial velocity components of X1 represent inlet impeller. For centrifugal compressor without the inlet guide vanes, the flow enters the impeller eye, axially or radially.
Both actually and radially.
So it enters axially. Next, by considering the centrifugal compressor, please choose the following option. Beta 2 is 90 for backward vanes, less than 90 for forward vanes, greater than 90 for radial vanes, or option C is correct here. For beta 2 is 90 degree for radial vanes, less than 90 for backward vanes, and greater than 90 for forward vanes. For centrifugal compressors, which of the following component is responsible for decreasing the temperature and increasing the entropy respectively? Decreasing the temperature and increasing the entropy. Accelerating nozzle and inlet gradients, or impeller, diffuser, or volute. So option A is correct. For the given expression of flow coefficient of centrifugal compressor, identify the right option. So flow coefficient is x by plate velocity. What is x? Absolute velocity, ideal velocity, relative velocity. Radial velocity is right. For flow through an axial flow compressor stage, as given in the following figure, which parameter do curve 1, curve 2, and curve 3 represent? So we have a first rotor, and then a air gap, and then we have stator. So which also following represents a curve. So can you say this? We have static pressure, static temperature, tangential velocity, or static pressure, stagnation temperature, and absolute velocity. So here across the rotor, both the static pressure and stagnation pressure increases, and also the absolute velocity also increases. In the air gap, it will be constant. All the parameters, three parameters, will be constant. And when in the stator, the stagnation temperature remains constant, but static pressure will increase. So this option A is right. So uh, so this is static pressure. This is stagnation. And this is tangential velocity. Static pressure will increase in both rotor and the stator. Stagnation temperature will increase only in the rotor, because that is where we impart some energy to the fluid, and later there is no energy transfer to the fluid. Tangential velocity will increase in the rotor, but in the stator the velocity element is converted to pressure element. So that is why in the tangential velocity decreases in stator. So curve 3 is right. Next question: which of the following is correct correlation between the blade loading coefficient and flow coefficient for an axial flow turbine? Here A alpha is Absolute velocity beta is a relative velocity blade angle. Suffix 2 and 3 represent the inlet and outlet condition for rotor. Blade loading coefficient. Blade load coefficient is flow coefficient into tan beta 2 plus tan beta 3. So option D is right. In thermodynamic analysis of flow through an axial flow compressor, which of the following statement is correct for the rotor? Stagnation temperature remains constant, static temperature increases, stagnation temperature increases, both stagnation and static temperature increases. So in a rotor, both the static and stagnation temperature increases. For flow through axial flow turbine, stagnation temperature across the nozzle decreases or increases or remain constant. So across the nozzle there is no increase in the enthalpy of the fluid, so stagnation temperature will be the same. That means it remains constant. For axial flow compressor, which of the following is assumption for free vortex condition? Static equilibrium, dynamic equilibrium, radial equilibrium, or chemical equilibrium? Radial equilibrium is right. Which of the following option is correct for flow across the rotor for axial flow turbine? Absolute velocity increases, relative velocity component decreases, axial velocity remains constant, all of the above. So all of the above is right. Next one, the impeller of a centrifugal compressor rotates at 20,000 rpm. The compressor delivers air at flow rate of delivers air at volume flow rate of 20 meter cube per second with pressure ratio of 4:1. The isentropic efficiency of compressor is 90%. The axial velocity of flow is 80 meter per second and is constant throughout. The outer radius of impeller, which has radial blades, has twice the inner one, and neglect the slip coefficient. Assume the ambient air condition are 1 bar and 303 Kelvin. Now we need to find the blade velocity at the impeller exit. So pressure ratio is given, that is P03 by P01, which is 1 plus eta C U square divided by Cp into T0 whole power gamma by gamma minus 1. So this is 4 and efficiency is given as 90% and U square is the unknown. Cp is not given, so it can be taken as 1005 as in for air, and T01 is given as 303 whole power 1.4 by 1.4. So we will have 1 plus 0.9 U square divided by 1005 into 303 is equal to 4 power 0.4 by 1.4. So then we will have 0.9 U square by 0.05 into 303 is 4 power 0.4 by 1.4 minus 1. Then U square is equal to into 1005 into 303 divided by 0.9, and U will be the square root of that. U square is equal to, first we can calculate this. this is 16, 164, 436, and square root of that is 405.5 meters. The inlet and outlet diameters of the impeller are dash. It is given that the outlet diameter is outer radius of impeller is twice as the inner one. So d by is equal to 2d. U is equal to 407. This is pi dn by 60 is 407. So with this we can calculate d. That is 60 into 407 divided by pi into 20,000. So this is 0.38 meters. So that means d is equal to d by 2, that is 0.3842 to the 0.9. So the answer is 0.15 and 0.38. Width of the blade at the inlet is in meters. So flow rate Q is equal to C1A1. So flow rate is given as 20 meter cube per second, and C is 80 meter per second into pi d1 b1. So b1 is equal to 20 by 80 pi into b1. So this is 20 divided by 80 pi into 0.5. So this is at the inlet, so it's d1. So this is 0.4. Next is a single stage axial flow compressor caters a small pressure rise because it experiences adverse pressure gradient, favorable pressure gradient, blade failure due to high impact flow or low blade height. A single stage axial flow compressor caters a small pressure rise because it experiences adverse pressure gradient. In axial flow compressor, the blades are facing the stalling condition due to large incident angle of flow, variation in mass flow rates, variation in rotational speed, all of the above. So it can happen, the stalling can happen because of all of them. In thermodynamic analysis of an actual axial flow compressor, the stagnation temperature of stator remains constant because no work interaction across stator, very less work interaction across stator, very large work interaction across stator. Stator blades are mobile because there is no work interaction across stator. For the given TS diagram, the following axial flow for an axial flow compressor, choose the following option: Zone B. Ideal work input, actual work input, losses during work input to the compressor, losses presence in rotor. This is actual work input. Next is for axial flow compressor, the work input to the compressor is small theoretically if the compression process is isentropic, adiabatic, isothermal, isobaric. The answer is isentropic. So only in isentropic process we will have the least amount of work. For the flow through the stage of axial flow compressor, which of the following option is correct regarding the absolute velocity of flow? So absolute velocity we will have generally rotor and air gap and then a stator. So absolute velocity will increase in the rotor and remain same in the air gap and then decrease in the stator. So that is option C. So here this is a rotor and this is a gap and this is stator. From the given figure of flow through the stage of axial flow compressor, choose the correct option for section BC, neglecting the gap between the blades. So if there is no air gap, which of the following will be BC? So BC would be stagnation temperature. Okay, so it will be all of them. Stagnation pressure will be the same, temperature will be the same, and this place for stator section. All of the above. For axial flow compressor, blade height dash towards the downstream of the flow. Continuously increases, remains constant, continuously decreases, none of the above. So it is continuously decreases. In case of axial flow compressor, the mean value of work done factor is continuously decreases, remain constant or increases as per the increase in number of stages. So it is continuously decreases. So more the stages will have less work to be done. Under the free vortex condition, degree of reaction of an axial flow compressor is dash to blade height. Proportional, directly proportional, inversely proportional, remains constant. Remains constant. For velocity triangle of a rotor, rotor of axial flow turbine, which of the following component of velocity decreases from inlet to outlet? Both absolute and well velocity. Choose the correct option for degree of reaction of axial flow turbine, where phi is flow coefficient, beta 1 is inlet blade angle of nozzle, beta 2 is inlet blade angle of the rotor, and beta 3 is outlet blade angle of the rotor. R is reaction of degree of reaction. 13 option is right. 14. In case of axial flow turbine with constant nozzle angle condition, which of the following option is correct for A? In the expression C W2 into R power sine 2A is constant. So outlet nozzle angle is correct. So I will just summarize the important formula to be noted to solve the jet problems. So propulsive efficiency is 2 by n plus Cj by U, and for Mach number is root gamma T, and jet velocity is sorry, this sonic velocity, and Mach number is given by flight velocity by sonic velocity, and thrust is given by m dot A plus m dot F into Cj minus m dot A into B plus exit pressure minus ambient pressure into area of the exit. And then we have specific thrust as F by n dot A. So specific thrust F is equal to F by n dot A. So in case of propulsive efficiency is equal to 0, that means U is equal to 0. Only when the flight is at rest, then we will have 0 propulsive efficiency, and thrust will also be maximum. And for propulsive efficiency is equal to 1, then U is equal to Cj, then there is no thrust.